Physical properties will start. So alkyl halides, first I will say you alkyl halides, then I will say you aryl halides. Alkyl halides, you will see the lower alkyl halides like CH3Br, CH3Cl, CH5Br, CH5Cl, the lower alkyl halides, they are generally gases. Still little bit higher one, up to C18, they are liquids, then still higher ones are solids. Okay, fine. Now, same thing in case of aryl halides also. The lower ones are, what you can say, the liquids, you can say that. Same thing in aryl halides. Next is alkyl halides. What you find is that if you see, that is the boiling point and the melting point. So listen very carefully here, the boiling point. The boiling point follows this order: Ri greater than Rbr greater than Rcl greater than Rf. We can say that. Now why? The reason is that is here this iodine, that is I minus, listen very carefully, the I minus is a stronger, what you can say, or polar substance then compared to what you can say F minus. Means this is more polarizable and this is less polarizable in nature. That is compared to what you can say I minus, F minus is non-polar in nature. Now you can say how it is so? It is having high electronegativity. Correct. So what you find is that even if it is having high electronegativity, so the bond length is very small in case of fluorine. It's very, very small in case of fluorine. So hence it is less polarizable in nature. Here the bond length is bigger because the size of the atom is bigger. So it is more polarizable. So what you find is that here Ri, got it, the bond length, it is quite bigger compared to that is Rf. So here for that particular purpose, as this is more polarizable in nature, listen carefully, very carefully, as I minus is more polarizable than compared to F minus, for that particular purpose, the boiling point of that is Ri is greater than that is Rf. So it follows this particular order, we can say that. I think you have understood this particular one, that I minus is more polarizable in nature compared to F minus. Remember it. It is more polarizable in nature compared to F minus, we can say. So for that particular purpose, as it is more polarizable, it pulls strongly the alkyl group. So more energy is required to break this particular bond. So hence alkyl iodide is what you can say having higher boiling point than what you can say alkyl fluoride. First of all, you must understand this. Next, after that, when the molecular weight increases, then the boiling point increases. That means I want to say I am having CH3Cl, I am having CH3CH2Cl, I am having CH3CH2CH2CH2Cl. Then what you find is that with the increase in molecular weight, the molecular size also you can see is increasing. The alkyl group, the size increases. So van der Waals force increases. For that particular purpose, the boiling point also increases. We can say that. Now, similarly, if the number of halogen atom is going to increase in case of chlorides, let me show you, number of halogen atoms means I am having CH3Cl, I am having CH2Cl2, I am having CHCl3, I am having CCl4, which is having the highest boiling point. This, then this, then this. CCl4 is having the highest boiling point, then this, then this. Alright, because the same thing, it is more polar in nature, this particular one, we can say that it is more polarizable. For that particular purpose, what you find is that it is having the highest boiling point. But the same thing is not true with fluorine, fluorinated compound. The same thing is not true. It is different for fluorinated compound, we can say that. Okay, because as the number of fluorine atom is going to increase, remember it, as the number of fluorine atom is going to increase, that means you are having CH3F, if you are having CH2F2, you are having CHF3. What you find is that in case of CHF3, the boiling point is going to decrease. Why? Because as the fluorine atom is increasing, non-polarizing atom increases. Alright, due to which the boiling point decreases, we can say that. Okay, otherwise, as the alkyl group increases, what you can find is that the boiling point increases because van der Waals force increases, the molecular size increases, or you can say the molecular weight increases. In this way, it behaves in this particular way in case of boiling point and melting point, we can say that. Now it is not melting because we are talking about the gaseous now, because already I said you the lower alkyl halides are gaseous, still higher ones up to C18 they are liquids, and still C18 they are solids. So we are not considering a C18, we can say that. Okay, fine. Now after that, what we will see is that if you see the solubility, that it is being soluble in naught. So if you see that dipole moment, then alkyl halides have got a very high dipole moment, a very high dipole moment. How much it is? Generally, the dipole moment ranges from 2.05 dBi to 2.15 dBi. So it's a very quite high dipole moment. So it should be highly polar in nature, correct? So it should be highly soluble in nature? No, it is less soluble in nature. Why? The reason is that alkyl halide fails to form intermolecular hydrogen bond with water. Again, I repeat, alkyl halides fails to form intermolecular hydrogen bond with water. It fails to form. Due to this reason, what you find is that it is less soluble in water, even if it is highly polar in nature. Moreover, another theory also goes that you know that solubility depends upon what you can say is that two energy. One is your hydration energy, another is your lattice energy. Here hydration energy is less than the lattice energy. What is hydration energy? Let me tell you. When you dissolve a particular compound in water, energy is released. That energy per mole is said to be as hydration energy. So when you dissolve alkyl halide in water, less amount of energy is released compared to lattice energy. So as hydration energy is less than the lattice energy, so hence it is insoluble even if it is highly polar in nature. Next is, if you see the stability, then alkyl halides, that is what you can say is that basically Ri is less stable in nature. For that reason we keep it in, if you remember it, if you have seen it also, that is in a lab we keep it in colored bottles. Why? Because if you keep it in light colored bottles, then in presence of sunlight it will give you RR plus I2 is released. We can say that. Due to which the resultant solution will be either brown or it will be violet in nature. For in case of alkyl iodide we can say that. So the stability is that alkyl fluoride is more stable in nature than bromide, then chloride, then iodide. Iodide is the least stable in nature. Why it is? Because the bond length is maximum. We can say that in case of Ri. Got it? The bond length is maximum. So hence it easily breaks, it cleavage easily. Got it? For example, this pen, let us say this is the bond length of Ri, and let us say this cap, this is the bond length of Rf. So which is more easily cleavageable? Definitely this one, this particular one, this pen, because it is what you can say bigger bond length, so it can easily break easily. For that particular purpose, what you find is that alkyl iodide are less stable in nature and they give brown or violet color on long standing air, we can say that. Okay. Now if you see, that is the next remains is your dipole moment. If you see that, then as I said, it has got a very high dipole moment and the dipole moment decreases from fluoride to iodide, we can say that. Okay. The same thing in aryl halides also. One more thing in aryl halides, let me tell you. Alkyl halides and aryl halides has almost got the same properties. The one thing is that in case of aryl halides, for example, if you are having that is para dichlorobenzene, if you are having ortho dichlorobenzene, then para dichlorobenzene will have high melting point, then ortho dichlorobenzene, or will have high boiling point, then ortho dichlorobenzene. The reason is that para means it is symmetrical. We can say that it is symmetrical. So as it is symmetrical, what you find? It is quite stable in nature. So as it is stable, more energy is required. So para dichlorobenzene will have high melting point or boiling point, then ortho dichloro or meta dichloro, we can say that. So this is one of the difference, or one more thing extra I should say that. And moreover, the dipole moment in case of aryl halides is slightly less. There I said 2.05 to 2.15 dBi. Here it is dipole moment is 1.6 to 1.8 dBi. The dipole moment slightly less in case of aryl halides, because aryl group is slightly less polar in nature, we can say that. Clear? So this is about your dipole moment. In case of solubility also same thing. Aryl halides are not soluble in water. Why? Because same thing, that aryl halides, you can see it is less polar than alkyl halides first of all, and aryl halides is not able to form intermolecular hydrogen bond with water, hence it is less soluble in water. So this is about your physical properties, we can say that. I said you. Now next is the most important is your chemical properties. We will come to the chemical properties. Okay. Now in case of chemical properties, you have to understand it very importantly. You have to understand it. Alright. So here the chemical properties is that it undergoes large number of reactions. First of all, alkyl halides. But one of the most important reaction is that it undergoes nucleophilic substitution reaction. It undergoes nucleophilic substitution reaction. Otherwise, see, halogen group is a very reactive group. So it undergoes large number of reactions. You will see it undergoes elimination reaction, it undergoes dehydrohalogenation reaction. But first we are going to start with what you can say is that nucleophilic substitution reaction. So the general reaction I am writing it out, Rx plus Nu minus, what you will get, Rnu plus X minus. So here we are going to take any nucleophile. Now any nucleophile means it has to be a stronger nucleophile than halogens. It has to be a stronger nucleophile than halides, we can say that. So what we can use it? Many nucleophile is there. OH minus, we are having Cn minus, we are having SH minus, we are having CO minus, we are having NH2 minus. In this way many are there, we can say is that. Clear? So many nucleophile is there, we will be using it here. So rather we cannot use a nucleophile here, rather I will be using a base here, rather I should say that. Achha. Now one thing you must know it here, that how will you know that which is a better leaving group and which is a stronger leaving group rather, or which is a poor leaving group. Okay, so this I am going to tell you in the next one. Thank you.